To shadow trajectories for 2x2 systems. Specifically, we're going to focus on with real eigenvalues and two linearly independent eigenvectors. Recall that if 2x2 matrix A has real eigenvalues lambda 1 and lambda 2 and linearly independent eigenvectors psi1 and psi2, then the system y prime equals ay has general solution y equals c1 times psi1 e to the lambda 1t plus c2 psi2 e to the lambda 2t. So we're working with shadow trajectories in this situation. So the question becomes, what is a shadow trajectory? So essentially, a shadow trajectory for a solution y equals a vector function y1 of t, y2 of t. A shadow trajectory for such a solution is essentially the graph defined by the parametric equations x equals y1 of t and y equals y2 of t. So essentially, we're plotting the dependent variables and we're not plotting t. The way we show time is just with an arrow to show time passing. We use arrows to show the direction of time passing. So right now we're just going to do some analysis of what happens with the various different cases for eigenvalues, and then we'll go ahead and do an actual example. So we have a variety of things that can happen with our eigenvalues. We could have two positive eigenvalues which are the same. So if we have lambda 1 equals lambda 2, both positive, again, we are still assuming we have linearly independent eigenvectors. xi1 and xi2. We will deal with the other case where we do not have linearly independent eigenvectors in a future section. In 10.4, we're sticking with these linearly independent eigenvectors. So we have general solution. Y is equal to C1 times Xi1 times e to the lambda 1t plus C2 Xi2 times e to the lambda 1t. Again, lambda 1 and lambda 2 are equal, so I'm just writing lambda 1. Note that we can rewrite this as C1 Xi1 plus C2 Xi2 times e to the lambda 1t. Because lambda 1 and lambda 2 are linearly independent, the C1 Xi1, since Xi1 and Xi2 are linearly independent, the C1 Xi1 plus C2 Xi2 spans the entire coordinate plane. Right? We can get any vector in that, it spans R2. And then e to the lambda 1t is just acting as a scalar. So it scales with time. And since lambda 1 is greater than 0, it implies that the scalar is increasing as time passes. I need to give myself a little more space. And we'll go ahead and draw what these shadow trajectories should look like. All right, so if we think about a coordinate system, I'm going to start off by drawing Xi1 and Xi2. Here they'll just be representative. So we'll draw two vectors, Xi1 and Xi2, which are linearly independent. So in other words, they're not just scalar multiples of each other. For a specific system, you will have specific Xi1 and Xi2. Now we know if C1 or if C2 is 0, we're just looking at scaling of that Xi1. And so what we get then is we essentially we'll just start at the origin working our way out, or start wherever working our way out. Sorry, we'll start at Xi1 and working our way out. And then as time goes backwards, we'll head back in towards the origin. Similarly, if we had a negative in front of Xi1, we would just be flipped. And we would work our way out. We're just following along the line that goes through the origin, travels along the vector Xi1, working our way out from the origin, since as time passes, the scalar gets larger. Similarly, if C1 were equal to 0, we would instead follow the vector Xi2 direction, or in terms of direction. So we will, as time goes to negative infinity, we would go into the origin, our scalar will go to 0. As time goes to infinity, we go out. And then we can go in the opposite direction as well, again, going away from the origin. And then, because Xi1 and Xi2 span the entire coordinate system, we could get any vector, and we're still just scaling as time passes. So essentially, we can take any line going through the origin, And as time passes, we just head away from the origin. So in the case that we have lambda 1 equals lambda 2, as time passes, well, in case lambda 1 equals lambda 2, we just have a bunch of lines going through the origin. And as time passes, we are moving away from the origin. So these are the shadow trajectories for a representative set of solutions. We can see essentially what the pattern is for any type of solution. Next up, we will look at the case where lambda 1 is less than lambda 2, both being positive. So again, we will have general solution. Y is equal to C1 psi 1 e to the lambda 1 t plus C2 psi 2 e to the lambda 2 t. This time around, we cannot just pull out an e to the lambda 1 and be left simply with C1 psi 1 plus C2 psi 2, since we do have different eigenvalues here. Note since both lambda 1 and lambda 2 are positive, we have e to the lambda 1t and e to the lambda 2t go to infinity as time goes to infinity, and e to the lambda 1t and e to the lambda 2t go to negative infinity go to 0 as t goes to negative infinity. So if we go backwards in time, we'll head to the origin. As we go forwards in time, we'll head off to infinity, or off to the edges of our system. Furthermore, since lambda 2 is greater than lambda 1, the e to the lambda 2t will overpower e to the lambda 1t as t goes to infinity. So the C2 psi 2 e to the lambda 2t will win out as t goes to infinity. On the other hand, C1 psi 1 e to the lambda 1t will win out as t goes to negative infinity. And what I mean by will win out, I simply mean that in the C2 psi 2 e to the lambda 2t will go to infinity faster. So we'll kind of follow that pattern faster. And then it will have the scaling of the vector will be larger, and so that vector will rule out. Similarly, e to the lambda 2t will go to 0 faster as t goes to negative infinity. So once again, the C1 psi 1 e to the lambda 1t will overpower, since it will not go to 0 quite as fast. Once again, I did not give myself enough space. Let me do that quickly. Continuing on, sketching our shadow trajectories. We draw our coordinate system. Once again, I'm going to draw a representative Xi1. And a representative Xi2. So when we initially start out, oh, sorry, my screen's not updating. Try this format. So we have our Xi1 and Xi2 representative vectors. Again, as we go backwards in time, we'll head towards the origin and we'll be following the C1 Xi1 e to the lambda 1t. So essentially what this means is we start off, actually we'll start off with a C1 equaling 0, C2 equaling 0. Okay, so if C2 equals 0, we just follow the vector Xi1 heading outwards from the origin, or we go in the exact opposite direction, heading outwards from the origin. If Xi2, if C1 is 0, then we just have C2, so we'll follow Xi2, heading outwards from the origin, or going in the exact opposite direction, heading outwards from the origin. Again, for any other solution, we'll start off more or less following along with Xi1, since the C1 Xi1 e to the lambda 1t wins out as we head in towards the origin. And then we'll end up following the direction of Xi2. So we'll start off kind of, let me do this in another color. We'll start off more or less following along Xi1 and then veer outwards until we more or less are going in the direction of Xi2, but shifted in and over. So it looks kind of like part of a parabola tilted around. We start off kind of flat with Xi1 and then arch our way around until we're running somewhat parallel to Xi2. We'll do this in either direction. Kind of heading around. Again, we start off kind of running along Xi1, either above the line defined by Xi1 through the origin or below. And then we keep on that side of our line through the origin following Xi1, eventually wind up running curve around until we run parallel or close to parallel to the line defined by Xi2 through the origin. All right, next case, we're looking at the case where lambda 1 is 0 and lambda 2 is positive. So once again, we have general solution. Y equals, in this case, it's just C1 Xi1. There's no e to the lambda 1t since lambda 1 is just 0. And then we'll have plus C2 Xi2 e to the lambda 2t. So note the C1 Xi1 is just constant. It doesn't change with time as time passes. So the C1 Xi1 does not change with time. And that means it does not go to infinity, nor does it go to 0. And so it does not head out or in as time passes. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . The C2 psi2 e to the lambda 2t is the part where time passes. Essentially, what we get is the C2 psi2 e to the lambda 2t. We're just scaling a vector, right? So and it just creates a line. So together, these just create a line. The C1 psi1 essentially tells us where we start as for the line. And then the C2 psi2 e to the lambda 2t tells us how we go from there as time passes. Again, the e to the lambda 2t goes to infinity as t goes to infinity, and goes to 0 as t goes to negative infinity. So essentially what we get is we will start along the line C1 psi1, since that part doesn't go away, and then we will head parallel to the line defined by C2 psi2. So if we draw our coordinate system, again, we'll pick representative vectors for psi1 and psi2. Psi1 will still draw the line through following along the vector psi1 through the origin, but that line will not have any arrows on it, because that line, as time passes, the points just stay still. Then what we will get from there, oh, I meant to do that in another color. I apologize. Okay, let's put our coordinate system back in and do this in a different color. So again, along psi1, we just stay constant. Along psi2, going from the origin and then just following straight along the scaling of psi2, we will head outwards as time passes. And then what we get is all other solutions will just be lines running parallel to the vector psi2. And we will head outwards from the line defined through the origin heading along psi1. So the psi1 vector line tells us where each solution begins. If time went to negative infinity, or where it comes from, assuming time went to negative infinity. And the psi2 vector essentially is telling us our slope. This is the last case where it's completely new. The following cases will just be mirroring what we just did on the positive values for negative eigenvalues. So our next case will be the case where lambda 1 is negative and lambda 2 is positive. So again, our general solution is y is equal to C1 psi1 e to the lambda 1t plus C2 psi2 e to the lambda 2t. Note that e to the lambda 1t goes to 0 as t goes to infinity, since lambda 1 is negative, and goes to infinity as t goes to negative infinity. Similarly, e to the lambda 2t will go to infinity as t goes to infinity, and will go to 0 as t goes to negative infinity, since lambda 2 is positive. So essentially what we get is these do not go to 0 at the same time, so we do not have a case of coming from the origin. We'll start off following along. As we go back in time, we'll follow along psi1, heading out away from the origin. And as we go forwards in time, we'll follow along psi2, heading away from the origin. So what we get is, as we go backwards in time, we'll follow along psi1, heading out from the origin. Right. Psi1 will be scaled by increasing the larger numbers as time goes backwards. And as we go forwards in time, we'll follow psi2 away from the origin. Once again, I did not give myself enough space, so I'm going to go ahead and do that quickly. I'm drawing our coordinate plane and putting in our shadow trajectories. Once again, we will draw representative vectors psi1 and psi2. We will have solution along psi1. So drawing the line through the origin, following the direction of psi1. This one, as time passes, the scalar heads towards the origin, or the scalar heads towards 0. So in this case, we'll start off at the outskirts, heading towards the origin as time passes, as we follow along psi1. Drawing the line through the origin following psi2. This time around, as time passes, we head away from the origin, since our scalar goes to infinity as time passes. And then you can see the shape kind of already forming just following those arrows. We get things that essentially look like hyperbolas. We start off following along psi1, head towards the origin. As we head in, we curve around to then follow along psi2. So we start off following along psi1 from far away. As we head towards the origin, we curve away from the line along psi1 to then follow along the line for psi2. So we get something that kind of looks like having hyperbolas in both directions. So these are the shadow trajectories for the case where we have one negative eigenvalue and one positive eigenvalue. Note, we don't have to really pay attention to how they compare in terms of absolute value, all that matters is we know which eigenvector corresponds to the positive eigenvalue and which eigenvector corresponds to the negative eigenvalue. Going forward, in the case where lambda1 is less than lambda2, with lambda2 equaling 0, so we have lambda1 negative, lambda2 equals 0. This will kind of parallel the case with 0 equaling lambda1 and lambda2 being positive. And we're just kind of flipping the signs here. It's just in this case, we'll head e to the lambda1t will go to 0 as time passes. So we have y equaling c1 psi1 e to the lambda1t plus c2 psi2. There's no e to the lambda2t since lambda2 is 0. As time passes, e to the lambda1t will head towards 0. And the picture we wind up getting if we draw our representative psi1 and psi2, this time around it was psi2, which was our constant. So any scalar of psi2, we'll draw the lines going along psi2 through the origin. That's going to just be constant. Points don't travel along that line. If we follow the line through the origin following along psi1, because lambda1 is negative, we're going to head in towards the origin. And then all of our other curves, because that psi2 component, C2 psi2, is just constant, that's essentially acting as where our line starts. And then we have the C1 psi1 e to the lambda1t. Psi1 is acting as our slope. So we'll just have a bunch of lines that run parallel to psi1. And this time around, as time passes, we actually head in towards the line that's through the origin along psi2. So in the positive parallel case, we headed away from the line. In the negative case here, we head towards that line. Next case, lambda1 less than lambda2 less than 0. This will parallel the case with 0 less than lambda1 less than lambda2. Once again, we will have y is equal to c1 psi1 e to the lambda1t plus c2 psi2 e to the lambda2t. We will have e to the lambda1t and e to the lambda2t both go to 0 as t goes to infinity. Since lambda1 and lambda2 are both negative, they both go to infinity as t goes to negative infinity. Because lambda1 is further from 0, e to the lambda1t will go to 0 faster. And so the psi2 component will win out as t goes to infinity. And then e to the lambda 1t will also go to infinity faster as t goes to negative infinity. And so the psi1 will win out as t goes to negative infinity. So putting this together, I apologize, I still need a little more room. I'm just going to squeeze this in this time around. Putting these together, once again, we draw a representative psi1 and psi2. Drawing the lines through the origin, traveling perfectly along psi1. That will head in towards the origin as time passes. Drawing the line along psi2 through the origin. Again, we'll head towards the origin as time passes. Our remaining curves, as we go to, as time goes backwards, we come from psi1, running parallel to psi1. And then as time goes to infinity, we wind up following along psi2. So we'll start off, I'm going to actually start off sort of at the end of time and work my way backwards. Starting off at the origin, we start off following along psi2. Then we'll curve away and head towards being parallel to psi1 as time goes backwards. Again, starting at the origin, we follow along psi2. We head to run parallel or close to parallel to psi1 as time goes backwards. So this graph should look very similar to what we saw before. This time just heading in towards the origin. Notice psi1 had our sort of larger absolute value for our eigenvalue, right? Lambda 1 had our larger absolute value. The parabola kind of opens up around the line along psi1 here. Whereas if we looked at the parallel case previously, Lambda 2 had the larger absolute value, and so the parabola opened up around psi2. It's not quite a parabola, but it looks more or less like one. All right. The last case we're going to look at is the case where lambda 1 equals lambda 2, both negative. This will parallel the case where lambda 1 equals lambda 2, both positive. So again, essentially what we wind up with is y is equal to c1 psi1 plus c2 psi2, the whole thing multiplying e to the lambda 1t. The c1 psi1 just spans the entire R2. And that e to the lambda 1t is scaling. Lambda 1 is negative here, so this will go to 0 as time goes to infinity, and goes to infinity as time goes to negative infinity as we go backwards in time. So in this case, we get essentially what we had before. We have our representative eigenvector for psi1 and psi2. We draw our lines through the origin along those vectors. This time around, we head inwards as time passes. And then all other solutions Again, will just be lines along any other vector, whatever vector we get from C1 psi1 plus C2 psi2. So we can just draw a few other lines through the origin. Again, as time passes, we head towards the origin. And those form a representative set of shadow trajectories. So this is more or less the various cases we can land on. Let's go ahead and do one example. We'll go ahead and sketch the representative shadow trajectories for the system y prime equals 1, 3 for a first row, 0, -2 for a second row times y. So again, we need to find our eigenvalues. We are working with a triangular matrix, so you can take the shortcut, or we can just do 1 minus lambda, 3, 0, -2 minus lambda, take the determinant of that, we should get 0. This is just 1 minus lambda times -2 minus lambda is equal to 0. And we wind up getting lambda is 1 or -2. So this is the case where we have opposite signed eigenvalues. So this is the lambda 1 less than 0 less than lambda 2 case. For our eigenvectors, for lambda equaling 1, we are looking at the augmented matrix 0, 3, 0, -3 with augmentation 0, 0. This tells us that psi2 must be equal to 0. So the vector we can pick for our vector psi1 to be, or our vector for psi in this case, just to be 1, 0. For lambda equaling -2, we are looking at 3, 3, 0, 0, and then with augmentation, the 0 vector. We wind up getting the psi2 as just -psi1. And so we could pick our vector to be 1, -1. So we have y is equal to C1 times 1, -1, e to the -2t plus C2 times 1, 0, e to the t. So what we're going to do here is we just draw our coordinate system. We draw the two representative vectors. So we have the vector 1, -1, and the vector 0, 1, 0. So we have our horizontal axis is going to be one of our lines. And then the line y equals -x will be our other line. Along 1, 0, e to the t will go to infinity as time passes. So we are heading out from the origin. Along 1, -1, e to the -2 will head to 0 as time passes. So we will be heading into the origin. And then we just follow along what these arrows show. So we'll start off along the 1, -1 line, and then curve around to follow the 1, 0 line as time passes. So that is how we go about finding the shadow trajectories for a 2x2 system.